Okay, so how is everyone today? Good, I hope. Okay, so there's these 3 written homeworks due. The last 2 classes, not most people, that was totally normal, but a handful expressed surprise that there were 3 due today. Okay, so I always send a message when there's a new one, and then the due date is always posted on the top of every one of those pages. So they're due when they're due. Now, this one time I'll accept if you forgot to do one of them. If you do it today and get it to my office by the time I leave at 2 p.m., then I'll accept it. Otherwise, they're due when they're due. Aside from these 3. Okay, other things that are due is there's online homeworks that are some of them are already due. They were due on Wednesday. There's one due tonight. Very good. There's a quiz with no math exercises due tomorrow, but you may have already done it. Any questions about any of that? Yes? Correct. You log on to the Testing Center webpage. They have a reserve a seat clicky thing. You click on it, you reserve a seat, you say, I'm so-and-so, here's my photo ID, I'm here for quiz, whatever.
And they're open tomorrow.
They are open tomorrow. But I don't know what their hours are, so you ought to check that. I think they're open from essentially all day, but don't quote me on that. Monday morning at 8:30 a.m. will be the first quiz. Will be the opening of the window of the first quiz that actually has math exercises on it. So you'll be able to take that quiz all week, just like the current quiz 0 that's open. Yes?
So quiz 0 is the only quiz that's due
Tomorrow.
Okay, sorry.
There's going to be 1 quiz per week from now on to the end of the semester. Other questions? Okay. So then we've turned in 5 written homeworks, 0 through 4, but 0 didn't have any exercises on it. This afternoon, I'll post keys to written homeworks 1 through 4. And there'll be PDFs and there'll be videos. You should have a look. Because besides doing that this afternoon, I'm also going to make quiz 1. And it will be in principle quite similar to written homeworks 1 through 4. So it's probably reasonable to say the optimal strategy is to study those keys. Another thing you might have noticed is that I did all of this last semester, and there's lectures of all the college algebra. There's videos of all the college algebra lectures last semester, and keys for quizzes and written homeworks for that matter, all still posted on YouTube. You're more than welcome to look at them, by all means. However, the schedule is slightly different between this semester and next semester. This semester and last semester. So, don't get caught in the trap of thinking, I'll just last semester I'll look at the videos corresponding to quiz 6, and quiz 6 this semester may not correspond to quiz 6 last semester. Okay, good. Any questions about any of that? Let's get to it. So last time we were talking about square roots and things. So now we're talking about, so this is section 1.3, continued. And we are now talking about the following. So I need to make 2 remarks. This is the general definition of radicals. Radicals. And the definition breaks into 2 pieces. So first we'll talk about the even half of the definition. The following are equivalent. This is in height. 1. Y to n is x. N is even. when y is greater or equal to 0. So there's a certain set of conditions. This is equivalent to the following. Y is the nth root of x. So now that looks just like square root, except unlike the square root, it's holding up a little n on its hand, you might say, whereas the square root wasn't holding up anything at all. Okay. Notably, didn't explicitly state it, but it is nevertheless a logical consequence of what has been stated. What must be true about the SIGN of x? What must be true about it? Almost. Non-negative. Because, let's consider. Because n is even, let's consider an even number like, say, 2, and let's consider a positive number like 3. How about 3 squared? Do you observe that it's still positive? How about negative 3 all squared? Still positive, right? How about 3 with exponent 4? That's positive. How about negative 3 with exponent 4? Still positive, right? Because when you're considering a product of negative things, you can take the negative numbers in pairs, and then the negativeness cancels out, right? So negative 3 to exponent 4. Well, that's negative 3, negative 3, negative 3, negative 3. You take the first 2 negative 3s, that's a 9. You take the second 2 negative 3s, that's a 9. And then the product of those 9s is 81. So, what I'd like for you to observe, that because n is even, x is necessarily non-negative. Okay? So that's the case for even radicals. Such radicals are said to be even, so they're even radicals. Okay, then the other case is the odd case. Now the following are equivalent. 1. So we start out just like 1 in the even case. We start out with y to n is x. And then we say n is odd. And now I'm just going to leave off that entire other part. So notably, what's being left off? In comparison to that one? Y being non-negative. It's just being left off. And then 2. Y is the nth root of x. So now, let's consider. If y, let's take an odd number. So how about 3? So we're going to consider exponent 3. Let's take a positive y. So how about 2 with exponent 3? What is that? It's positive 8. So positive 2 cubed is positive 8. How about negative 2 to exponent 3? What is that? Negative 8, right? Because negative 2 multiplied by negative 2 is positive 4, and then multiplied by another negative 2 is negative 8. So the fact that n is odd, means that, okay, now sign, SIGN, is not a big consideration. So what this means is that in the odd case, in odd means that x and y have any sign. Okay. So for example, how about the fifth root of 32? Well, what is that? Fifth root of 32. That is to say, you're looking for a number such that when you multiply it by itself 5 times in a row, you get 32. 2 will do it, right? Because 2 times 2, that's 4, times 2 is 8, times 2 is 16, times 2 is 32. The product of the fivefold product of 2's is 32. So the answer is 2. How about the cube root of 64? Cube root of 64. It's 4. It's 4. Because 4 times 4, that's 16, right? And then multiplied by another 4, well, that's 10 4s and 6 4s. So that's 40 and 24, that's 64. Okay, so the answer is 4. How about, what is the fourth root of 81? We did this out loud just a couple minutes ago. What's the fourth root of 81? 3. I think we can all agree that 9 times 9 is 81, right? 9 times 9 is 81. And then each one of those 9s has a 3 and a 3. So that altogether there's 4 of them. So 3 times 3 times 3 times 3, that's 81. So the fourth root of 81 is 3. How about the fourth root of 16? Two. Good. How about fourth root of negative 16? What's the correct way to respond to this prompt? What's the correct response? It's not defined. This is not defined. So now, why is it not defined? Well, so this is an even radical. It's radical 4. Okay, and then we go to the definition of radicals, to the even section, and say, well, we observe that a logical consequence of the definitions is that x, the thing being put in, the argument, has to be non-negative. Can you put a negative 16 in there? No, you can't. It's not defined. So the argument to even radical must be non-negative. Okay, how about the cube root of -8? What do you think? So in the first place, is this defined? So is it defined? Some of you are a little squeamish because we just did this one where you had a negative inside of the radical and we said no, no. So is it defined? It is. It is defined. So notice that this is an even radical. Fourth radical, radical 4. 4 is even, so this is an even radical. This is an odd radical. It's radical 3. 3 is odd. That means that this one, notice that we said up here that odd radicals means that the input x and the output y can have any sign. So can you do cube root of -8? Sure. What is the cube root of -8? Not 2. -2. Because it's not 2, because 2 times 2 is 4 times another 2 is 8. Whereas -2 times -2 is positive 4 times another -2 is -8. Okay, so this right here is that, and then the argument to an odd radical can have any sign, which is the first one, or that one, I mean. Okay. Any question about this? Okay. So here's another version here. So, for example, I want you to factor out from the radical as much as possible. Assume variables are positive. Okay. So, if you recall on Wednesday, we did some simplification of radicals. For example, we said that, can you simplify the radical square root of 16? Sure, right? The 16 can come out of the square root. How does it come out? As a 4, right? Because 16 is 4 squared. Okay. So now the reason why that works is because square root is second radical. It's radical 2. So when things come out of square root, they come out in pairs. When things come out of the cube root, they come out as triplets. When things come out of fourth root, they come out as quadruplets, etc. So let's have an example of doing this. So how about cube root of 16 x to 7 y to 5. Okay. 16x to 7y to 5. So since this is the first time, it may not be entirely clear what I'm requesting, so I'll do the first step. So what I'd like for you to observe, because this is cube root, I want to make things into groups of 3. Now 16 we've already said is 2 to 4, right? 2 to exponent 4. So I'm gonna write it in a slightly strange way. I'm gonna say, well, it's 2 to exponent 3 multiplied by another 2, and then x to 7, y to 5. So all that this part is just a strange way to write 16. It's 16. But what I want you to observe is that now I've got these twos right here, tripled up. They're tripled up, which means that they can come out of the radical. Because it's third radical, and I've got 3 of them, that means that they come out. So 2 cube root, and then 2 x to 7 y to 5. So specifically, those 2's came out, that 2 cubed came out as a 2. Just like when you take 16 out of a square root, what does it come out as? 4, because it's the 4 squared coming out as a 4. This is 2 cubed coming out of the cube root as a 2. Okay, now one more step, and I think the pattern will probably become clear. So now notice we've got a bunch of x's. We've got 7 of them, all in product. So I'm going to rewrite those x's in kind of a strange way. I'm going to say, well, that's x cubed multiplied by x to 4 and y to 5. So I can do that because of the laws of exponents that we've already discussed. X to 3 times x to 4. Notably, now, I've got that triple of x's. It's a triplet of x's. And this is a cube root. This is x cubed and it's cube root. So that x cubed can come out now. And when x cubed comes out of the cube root, what will it come out as? X. But now that I've done that step, I hope you can see, oh, wait a second. We could have taken out more x's. There was more to take. Because if what we're doing is taking out x's in groups of 3, couldn't we have taken out another group of 3? Yeah, there's 4 of them right there. Could we get another group of 3 to come out? Sure we could. Let's do that. So that's the first x, and then here's another x that came out. 3, 2. So what we're doing is we're taking some more of these x's, they're coming out. Now when we do that, are there any x's left over? There's 1 x left over, right? So it has to remain, right? You're still inside the radical there. 1x. X to 1. So how about, so any question about this, getting to here? Now what else can we do? Okay, so we could write x squared, I'll do that, but, and I agree entirely, but I was thinking of something else within the radical. Right, there's 5 y's in product. We can take out a group of 3. If we were to take out a group of 3, how much would remain in there? 2, right? We'd still have y squared. So let's do that. So this would be 2 x squared y cube root 2x y squared. Because what we did is we said, here's y to 5, so I'll take out y cubed, and it comes out as a y, and then there's 2 left over. Any question about this? So this is what I meant when I said that when dealing with cube roots, things come out as triplets. When dealing with square roots, things come out as twins, doublets. If it was 5th root, things would come out as quintuplets. Any question about this? Okay. More? Remark. The following are equivalent. One. Y is the nth root of x. 2. Y is x to exponent 1 divided by n. So what I mean by this is that x raised to exponent 1 divided by n is just another way to write nth radical. They mean exactly the same thing. Okay, they're synonyms. However, remember that for radicals, we had the parity part of the definition, right? Which means that every bit of parity, even in oddness, that affects this one also affects this one. So even odd considerations are still here. So for example, I could ask, well, how about 64 to 1/3? What is this? So in the first place, how do you express this as a radical? Cube root of 64. So these two things are just synonyms. But what is the actual numerical answer for? Any question about this one? How about negative 125 cube root? So in the first place, is that even defined? It is defined, right? Because this is equivalent to odd radical cube root negative 125. So odd radicals, those are the permissive ones, right? The ones that take any argument whatsoever. Positive, negative, whatever. Even ones, these are the ones that have a problem with negatives. So then this is, so what is the answer? Negative 5. Okay, how about negative 81 to 1/4? What's the correct response? Not defined. Because, how do you write this as a radical? 4th root of negative 81. Okay, so then if it wasn't clear before, it's clear now. This is an even radical. What must be true about the arguments to even radicals? Must be non-negative. So the correct response here is that this is not defined. Defined has an N in there. yet 81 to 1/4 is what? 3. Any question about this? Okay, next. The following are equivalent. One. Y is x to 1 over n to m, like so, with n and m integers having no common factors. So what I mean is, for example, we could have 5 and 3. 5 and 3 are both integers, and 5 and 3 have no common factors. But I'm not talking about 10 and 6. Because 10 and 6 are both integers, that's good. But 10 and 6 have a common factor of 2. That's bad. So we're not talking about that. Okay. So that statement is equivalent to this statement. Is equivalent content to this one. X to m over n. So for example, I could say, okay, I want you to evaluate 64 to 7 over 6. Now I want you to do this without the aid of a calculator. No calculator. So, how do you go about doing it? So you have to use this representation here. You say, okay, according to the definition, this should be 64 to 1/6, and then raise that to 7. So now 64. So you're in a college algebra class, and it's really in your interest to know all of the powers of 2 up to like as high as you can go. Preferably up to like 14, 2 to 14. In particular, I hope it's clear to you that 64 is a power of 2. Like when you read about, oh, this is my PlayStation has a 64-bit processor, or my Xbox has a 64-bit processor, and 64 shows up all over the place. Why does it show up all over the place in computing? It's a power of 2. So what is 64 to 1/6? 2. Right? And then what's 2 to 7? Well, if 6 2's is 64, then 1 more is 128. Okay. How about negative 125 raised to 4 over 3? So in the first place, at least momentarily, there should be a question. Is this even defined? So is it defined? It is defined. Because according to definition, this is, you take negative 125, you do cube root of that, and then raise that to 4. So the question is the cube root of negative 125 defined? It is, because cube root is an odd radical, and odd radicals are the permissive ones. So what is the cube root of negative 125? Negative 5. And then what is, so now to exponent 4, what is negative 5 to exponent 4? Well, it would have to be 5 times 125. So that's 500. And then 4 more 25s is 600. And then 1 more 25 is 625. Okay, without the aid of a calculator. Now I'd like to point out that this particular exercise, I suspect that your calculator would choke trying to do it anyway. Because if you wanted to type this into your calculator, in calculator speak, you'd have to type in parentheses negative 125 and then caret 4 divide 3. So that's how you get your calculator to do it. Let's see what my calculator says if I type that in. Okay, so negative 125 to exponent 4 over 3. And the calculator says, wah, wah. So, the reason why is because what the calculator is actually doing, is it's doing 4 over 3, calculating 4 over 3, and it doesn't know how to reckon 1.33333, which is 4 over 3, as an even or an odd number. And to be safe, it's saying, no, I refuse. Won't do it. But of course, that's not according to our definition. Right, this one. Okay, good. Any question about this? Okay, new section. Now we're in section 1.4, which is called polynomials. Okay, first definition. Let A be in the reals, and let N be in the naturals. Then an expression of the form A multiplied by x to n, this is called a term. It's called a term. This number in the front, its name is the coefficient. Coefficient. This number and the exponent is called the degree. Okay, so I could give you an example. I could say, well, how about 5x to 3? What is the coefficient? Five. What is the degree? 3. Any question about this one? Okay. How about if I was to give you negative 7x? What is the coefficient? Negative 7. What is the degree? 1. It's degree 1 because that x has the implied exponent 1, right? X is x to 1. So the degree is 1. How about this one? 7x to 3/2. Now how do you respond if I ask you to tell me the coefficient and the degree? Now the correct response is, that's not a term. It's not a term. Why is it not a term? So the correct response is that this is not a term. And why is it not a term? It's not that. It's not the x. It's that the degrees must be natural. This number, 3/2, is not natural. It's not I'm not moralizing against 3/2. I'm just saying it's not a positive integer. Okay. So polynomial. A polynomial, which I'll from now on always write as poly. A polynomial is a sum of terms and possibly a constant. So, for example, (5x squared minus 3x). Is this a polynomial? Yeah. Because that's a term. What's its coefficient? What's its degree? 2. That's a term. What's its coefficient? -3. What's its degree? 1. And so then that's a sum of such terms. So, yep, that's a polynomial. How about 5x squared minus 3x plus 4? Is that a polynomial? Yes. Why does that fit into the definition of a polynomial? Because and possibly a constant. So here's the sum of terms and a constant. So yes, this is a polynomial. How about 7 square root x plus 9? Is this a polynomial? Nope. Why is this not a polynomial? Right, this thing, square root. Square root is second radical. So second radical is equivalent to what fractional exponent? Half. So this thing is not a term. And because this thing is not a term, this sum is not a polynomial. How about 12? Is this a polynomial? Yes. This is a constant polynomial. is the sum of no terms and possibly a constant. So, yes, it is a polynomial. So, polynomial. Now, we're going to use polynomials all semester long. And we're going to talk about them all the time. So in order to talk efficiently about them, we have to have some jargon. And all that jargon means, jargon is a set of vocabulary words that's common to a specialized circumstance. So, for example, medical doctors have a great deal of jargon. So if I was to gash my leg and go to the hospital, I'd probably tell my family members, "Oh, I got stitches." This is not what physicians say. What do they say? Sutures, right? That's part of the physician jargon. We have jargon, all manner of jargon in math classes, and here's polynomial jargon. So if I give you a specific polynomial, say like this one, 6x to 4 plus 5x to 3 minus 4x to 2 plus 9, then each one of these is a term, so term, 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 and the constant. And each one of them has a coefficient, right? 6, 5, and negative 4, and then the constant 9. This one has its degree, 4, 3, 2, and then that's the constant. This specific one that we're going to pick out, this is going to be called the leading coefficient. That is to say, it is the coefficient of the term which has highest degree. So it's called the leading coefficient. And then this degree, the degree that is highest among all terms, this is called the degree of the polynomial. So for example, I could say, well, how about that polynomial? So the one that I gave up there. What is the leading coefficient? 6. And what is the degree? 4. Okay, what if I was to give you this example? If I was to say, how about 5x squared minus 7x cubed plus 39. Then what's its leading coefficient? Not 5. So what is it? Negative 7. Now, some of you are looking at that saying, now wait a second. It is quite clear that 5 is the number that is furthest to the left. And I agree entirely. But that's not what the leading coefficient is. What is the leading coefficient? It's the coefficient of the term of highest degree. The term of highest degree is the one in the middle. So I baited you to give me the wrong answer here where it doesn't count. Okay, so the leading coefficient is negative 7, and the degree is 3. Now that being said, when I give you exercises, you should check: are the terms in descending order? The biggest one, then the next, and then the next, and the next. You should check that. But when you give me an answer, I always require that you give me the terms in descending order of degree. You have to give them to me in that way. So that representation is called the standard representation. So the standard representation has terms in descending order of degree. So let's write this one. I know we're coming right up on the edge of time here. Let's write this one in descending order of degree. So this is how it was given. So 5x squared minus 7x cubed plus 39. So is it in standard representation? not currently. So how do we write it in standard representation? Right, negative 7x cubed, yes, plus 5x squared, plus 39. Now, the last thing for today. Notice that this is the degree 3 term, the degree 2 term, and the constant one, which is frequently referred to as the degree 0 term. So 3, 2, 0. And in a certain sense, you might say something's missing. What's missing? The degree 1 term is missing. So when I ask for you to give it to me in standard representation, this is the answer. But if I say I want you to give it to me in standard representation with zeros, then the answer is negative 7x cubed plus 5x squared plus there are 0 x's plus 39. So in the first half of the semester, I'm essentially always going to be asking for this one. But in the second half, there's going to come a time when I ask for this one because we're going to be performing a computation that occurs in rows and columns. And if you don't write the zeros in, then your columns won't line up right. So it'll be necessary to write it in that way at that time. Have a nice weekend.